In Lab 2, I will be exploring how the drag force, which is the force of the atmosphere, and the force of gravity affect an object's motion. The fundamental principles used were Newton's second law and the position function to predict the future motion. The objective of this lab was to observe an object falling straight down at relatively slow speed and analyze its motion in Tracker. I recorded a lightweight puffball being dropped. To build on the principles from Lab 1, I added the drag force, which is the force from the atmosphere, in addition to Newton's second law. Overall, my results showed that the computational model I used that accounted for the drag force was much more consistent with the observed motion than the model was with just gravity. Furthermore, the gravity model calculated that a much larger distance was traveled during the 0.499 seconds than what was actually traveled. As can be seen from the video in Tracker, the ball clearly speeds up as the video continues. This is shown by the larger increments between position markers in Tracker. The Tracker video shows that the final position of the ball is at negative 0.026 meters. Furthermore, it is important to recognize that the motion of the object is not as linear as was observed in Lab 1. To make my GlowScript model, I adjusted the starter code given in the lab to account for gravity and the net force. Using Newton's second law, I determined that the net force would be the sum of the two forces that are being considered in this lab, which are drag and gravity. From here, I determined that Fnet would be equal to negative mg plus the constant b times the object's velocity squared, as given in the lab's instructions. However, because in this scenario I neglected to account for the force from the atmosphere, the value of b was 0, so Fnet is just equal to negative mg. For the initial velocity input, I calculated the initial velocity from the first two Tracker data points and put this value into the model. I chose to analyze my video shortly after the beginning of the recording due to image issues to make the Tracker analysis flow better because the camera was shaking at first. The motion with gravity shows a similar curved shape. However, the ball is shown to travel much farther than it actually did, reaching negative 1.24 meters in the model as compared to negative 0.026 meters in the observed motion. In the next scenario, I account for drag in the model and found through trial and error that the value of b should be about 80 kilograms per second. Graphically, the model showed a much more linear motion. The drag force allowed for the final position to be much more consistent with the actual position at t equals 0.499 seconds, which was negative 0.027 meters compared to negative 0.026 meters. As can be seen in graph 1, the model with drag is a much closer estimate to the actual motion of a lightweight object than that with just gravity. This can be seen by comparing the blue and the gray lines at the top, where blue is the observed motion and gray is the model with gravity and drag. This makes sense because the velocity of the object is largely affected by the forces that act on it, and mass is a factor that affects the force. In this lab, it is evident that the force of drag has a significant impact on the motion of lightweight objects, so it makes sense that there is a drastic difference between the models with and without drag. To address question 1 about predicting a terminal velocity. Terminal velocity is the constant speed that a freely falling object reaches when the net force is 0. Going back to the results page to show my graphs. You can see from the position versus time graph that the slope is linear towards the end of the observed motion and is relatively linear the entire time from the model. Because it is linear, you can assume that the velocity is constant and that there is no force acting, which means that terminal velocity was reached. However, the drag model shows a motion that is pretty linear the entire time, predicting a terminal velocity much sooner than in reality. If the ball were to be thrown down, there would be an initial force that would cause there to be a significantly high initial velocity. When this is modeled in GlowScript, the drag force appears to exceed the force of gravity. However, they balance out over time, and a terminal velocity is indeed reached. It just takes a little bit longer than without the initial force. Overall, both the atmosphere and the Earth acted on the ball as it fell, but the force of the atmosphere does not have as much of an impact as gravity. Thank you.